Okay, let's continue with cooperation strategies using evolutionary and game theory. And here we address a very important and very famous example called the prisoner's dilemma. So the prisoner's dilemma describes a situation where two burglars got caught by the police, but they don't have really evidence against them, right? So what they do now, they would like to interview them, but separately in different rooms. And what they tell them is the following. They have two options, right? Either they could confess or they can stay silent, say nothing. And they know that the other burglar sitting in the next room will give them the same option. You see here the parallelism between this and the game we played before, right? So what the outcome is, if the prisoner one would say, I'm an honest burglar, I will stay silent, and so prisoner one will do what we would expect by real burglars, they would get both 2 years in prison. So here it's not the highest point that will win. The lower the years you have to sit in prison, the better it is. So here you see first strategy for prisoner one and one strategy for prisoner two. And this means 2 years for both of them in jail. Interesting it becomes, first what we say is if both they stay in prison, together they stay 4 years in prison. If you look at all the other numbers, if you compare it with them, it seems to be the lowest. So this is something where you would say they should agree on, let's do this one. It's only 4 years for us all. This is called also Pareto optimal, right? So the word optimal means, okay, this must be the strategies that both will choose, right? But what are with the others, right? So for example, if prisoner one knows that prisoner two will stay silent because he's honest, he could think, let's cheat about my friend here, then I only have to stay 1 year in prison. On the other side, betraying him means the prisoner two or the burglar two will get 6 years. In total, these are 7 years, right? More than the 4 that we had before. So there is an attempt from prisoner one to say, maybe I should do that. And the same, of course, is for prisoner two. If prisoner two assumes that prisoner one is the honest one, he could also say, maybe I'm betraying him, and then I only have to stay 1 year, and he has to stay 6 years. So for him, this option seems to be better. Now, as both are presented to the risk that they can be betrayed, what might happen is that they both will betray each other. Now, what you see here is they get the highest amount. They get 8 years in prison. But what you will see is, and this is something very important, in the end, they will choose to betray each other. The question is, what would you do, right? Would you also betray or would you stay silent? It looks so tempting to say I stay silent because the overall amount of years is too high. Maybe you know the other guy. Then we come back to the term cognition, and you would not, you would hate to put him in prison, and then you would really stay silent. And there are different opportunities. But if you play this game, this prisoner's dilemma once, betraying seems to be the best. And this is called the Nash equilibrium. And this tells you what is the best for you, and you will not like it, but the winning strategy is exactly that. And the Nash equilibrium says, what would prisoner 2 choose if she or he assumes prisoner 1 stays silent, right? Then it's clear you would choose this one. If you betrays, what would prisoner 2 choose if she or he assumes prisoner 1 betrays? It's also clear that's this one here. But what would prisoner 1 choose if she or he assumes prisoner 1 stays silent? Yeah, this is this one. And then you have two dominant strategies here. And this is the so-called winner situation, the Nash equilibrium, where both prisoners will betray each other. So this means no other player has an incentive to deviate from his chosen strategy. There's no better way than this what you can do. So prisoner 1 will say, I will stay here. It's either 1 or 4. There's no better I can do for myself. And prisoner 2 will do the same, right? So he will stay on option 2, betraying, and therefore this is the Nash equilibrium. In order to show you this, we will give you some more examples later, but first a summary. And here the question, if the best strategy in this prisoner's dilemma is not to cooperate, why do we talk about cooperation at all? You will see it later. And this is given by the fact that cooperation spawn maybe if we play the game again. So if the burglars are stupid and they get caught again and caught again and caught again, maybe they have a different strategy than if they get caught only once, right? We come back to that. There's a nice video. I put here a link. There's a movie about the Nash equilibrium, about the Nash. You can enjoy it. It's very funny, but be cautious, because the Nash equilibrium, the original Nash is proposing here, is not really a Nash equilibrium. Good. Some examples for you, some other games. Here we come back to the idea of points. We have two players, Alice and Bob. Alice points are in green and Bob are the one in yellow. Here's the question, what is the best outcome? Alice has two options, left and right, Bob up and down. So what would they choose, right? So the 2, 3 is a little bit only here. Here seems to be a lot of points here, but here even way more points. But this has nothing to say, because as we have seen before, even the prisoners, even they go only 4 years in prison, they have not chosen that one, right? So how would you like to find out the Nash equilibrium here? Or a question, is there Nash equilibrium? So the question is, if Bob goes up, what will Alice do? Now, Alice goes right? This is my bet. If Bob goes down, Alice will go right again. So this is the dominant strategy for Alice. Now, if we ask Bob, if Alice goes left, then Bob goes down. This is one. And if Alice goes right, Bob goes down again. This is the points here. And you see, these are 2 points chosen, and this is the Nash equilibrium. Even though it did not seem appealing in the beginning, again, this is the Nash equilibrium that both will choose. And we have a prisoner's dilemma in this game as well. Another example is given here, where you would do the same, Alice and Bob. You will see the points, the same question as I have done before. You can do it yourself. And you see there's no clear winner here. So here we don't have a Nash equilibrium. In another example, what we see here, we have one Nash equilibrium with a prisoner's dilemma again. And I give you another example, also more in detail, because sometimes the questions I did before, what would Alice do if Bob goes up and down? You can even do it in a different way, how to question it. And as some of the videos in the YouTube are given like this, that you don't get confused, I also put this. So Alice could say, I will start left, and the highest point on left is 9. So I choose the 9 here. If I go on the right, the highest point I can get is here, the 8, right? Now, Bob can take the upper strategy. 8 against 6 is 8. And if Bob takes the lower, this is the 1. So now what you see, what is here the Nash equilibrium? We have 2 Nash equilibriums in this game, right? Also the same given points. With that, I would like to come to cooperation strategies using evolutionary and game theory in repetitive games. Because before we had only one game that we played, like the prisoner's dilemma, but now we go on with playing the game multiple times.